Now we will prove the fourth property of simple and stiff functions. So that's fourth property, which states that chi of A union B, chi of A union B is equal to chi of A plus chi of B minus chi of A intersection B, which is the same as chi of A join chi of B. So in this property, I will prove first and first is equal to the third. So I will leave this as an exercise first equal to 1. Okay. So let's take the first case if x belongs to case 1. Case 1. If x belongs to A union B, this implies x belongs to A or x belongs to B. X belongs to A or x belongs to B. So then now let's find this chi of A union B of x, which is equal to 1, and the join of chi A and chi B, or you can say the maximum value of chi and chi B at x, which is equal to 1. It's by definition it's equal to maximum of chi AX chi BX. That's by definition. And here in this case, either x belongs to A or x belongs to B. If x belongs to A and not in B, then chi x is 1 and chi bx is 0. In that case, maximum value will be 1. And in the case if x is in B but not in A, then in that case this chi A is 0 and chi B is 1. So again the maximum value is 1. And in case x is in A as well as in B, this may be the case also, then in that case both the values are equal to 1, and hence the maximum value is also equal to 1. So in all the cases of this case 1, in all sub cases of this case 1, the maximum of chi AX and chi BX is equal to 1. So thus chi A union chi B is equal to chi A join chi B. Thus chi A union B is equal to chi A join chi B in this case. Okay? In this case they are equal. Now I will take another case, case 2. Case 2. Case 2 is if x is not in union. If x does not belongs to A union B, this implies x is not in A and x is not in B. So now in this case I will check the equality. Okay, chi of A union B of x is equal to 0, and this one chi A meet chi A meet chi A meet chi B of x, which is the maximum value, maximum of chi AX, chi A, maximum value of chi A of x, chi A of x, chi B of x. That's equal to 0 because both are equal to 0, as x is not in A and x is not in B. Thus chi A union B is equal to chi A join chi B in this case, in this case also, in this case also, and hence they are equal. Hence chi A union B is equal to chi A join chi B. So that proves this fourth property. Okay. Now, how we prove the fifth property of the characteristic function? That's chi of the difference is equal to chi A minus chi of the intersection. That's the fifth property. Chi of difference is equal to chi A minus chi of the intersection. So I leave this an exercise for you. So verify this. Verify. Again, take two cases if x is in a minus b, and in the second case, you take x is not in a minus b. And you will see that both the values are equal. Both the values are equal. Sixth property is if A is the disjoint union, if A is equal to union an and runs from 1 to infinity, where these ai's they are in they are subsets of x. Sorry, they are subsets of x. A given set. They are subsets of x. They are all subsets of x, and they are also disjoint. Okay. AI intersection AJ is phi for 1 less or equal to I, j less or equal to sorry, they are greater or equal to 1, both I and j, because it is an infinite sequence actually. Yeah. So both are greater or equal to with I comma j greater or equal to 1, and I is not equal to j. Then we show that chi of union is equal to sum of the chi's. Then we need to verify this. Chi of union means chi of A is equal to summation, and runs from 1 to infinity chi A. So this is again simple. You again take two cases if x is in A, and the second case if x is not in A. So let me verify this. So suppose case one. Case one is if x belongs to A, which is equal to the union an and runs from 1 to infinity, then x is in exactly 1 ak, because this is the disjoint union. Then there exists unique k unique k such that x belongs to ak, unique k. So therefore if it's in only 1k, therefore x is not in the other ai. X does not belongs to ai for all I not equal to k. So now you find the correct chi values. Now what's the chi of a of x? It's equal to 1 because x is in a. And what's the sum? This sum, you can see this sum chi of a and of x and runs from 1 to infinity. In this sum, since x is in exactly 1ak, so the k term of this sum is equal to 1, and the rest of the terms are equal to 0, because for the rest of ai's x is not in those ai's. So that means chi values with respect to these sets with respect to these ai's are equal to 0. So this means this sum is also equal to 1. Thus chi a is equal to the summation and runs from 1 to infinity chi a n, chi a n in this case, in this case. Now, second case, I will leave this an exercise for you. Case second. But case second if x is not in. Case second. If x does not belongs to A, then this implies uh, x is not in the union. That means x is not in each A. This means x is not in union an and runs from 1 to infinity, which implies x is not in an for all n greater or equal to 1 because it's not in the union. So therefore both chi ax equal to 0, and this summation is also equal to 0 because x is not in any an runs from 1 to infinity. It's also equal to 1. So you can say thus this chi a is equal to summation chi a n and runs from 1 to infinity. In this case also, in this case also. So hence they are equal. Hence this chi a is equal to summation chi a n and runs from 1 to infinity and runs from 1 to infinity. Okay, so that proves all the properties of the characteristic function. Next, we will define the simple function, then we define step function. Okay, simple function. So throughout this section, throughout this section, x as mu is a major space, is a major space. Okay, so it's a major space throughout this section. X as mu is a major space, and the functions are from x to r in this section. They are all real valued functions on the major space X. So let's define first simple function. A measurable function phi, a measurable function. It's first a measurable function. A measurable function phi from x to r is called a simple function. Is called a simple. Is called a simple. Is called a simple function if it assumes only finitely many values. If it assumes only finitely many values. Finitely many values. If the range set is finite set, actually it assumes only finitely many values. So that's the definition of simple functions. So we have examples we have step functions. These are not step functions. The characteristic functions, they are all simple functions. Example. Let's take example. Let A be a measurable. A be a measurable subset of X. A be a measurable subset of X. Then this function, then characteristic function of a which is defined by x is equal to 1 if x is in a and it's equal to 0 if x is not in a, is a measurable function. This function, then this function is a measurable, you can easily verify it because it is a measurable subset of x. This function is measurable, is a measurable function. So verify it, it's a measurable function. Also this function chi a assumes only two values, only two values, 0 and 1. It has only two values, 0 and 1. Thus it's a thus it's a measurable function and it assumes only two values. Thus it's a simple function. Thus chi a is a simple function. That's an example of simple function. Example of simple function. Also, you can say the step function. They are also simple functions as well. Step function is on any finite subset of R. They are always bounded subset of R. They are simple functions. They are simple functions. Okay. So now we discuss it's algebra. Actually, it is the sum of the sum of the simple functions and the product of simple functions. When you take the infimum and the supremum of simple functions, we will see they are all simple if we take the finite collection. Okay, so that's an exercise for you. If phi k 1 less or equal to k less or equal to n, or simple functions are simple functions, okay, then show that the first one is the summation k runs from 1 to n phi k is again a simple function, is again a simple function. And second one, the product k runs from 1 to n phi k is a simple function, is a simple function. And the third one is the infimum of phi k 1 less or equal to k less or equal to n, and the supremum of phi k 1 less or equal to k less or equal to n, or measurable, or a simple function, or simple functions. So this is an exercise for you. You verify these parts of the exercise. Okay. Now we discuss the representation of simple function. Okay. Now we will try to find out its representation. Representation of simple function. Okay. Representation of simple functions. Okay. So for this, I will take the only non-zero values of the assumed by the simple function phi. So let phi be a simple function. Let phi be a simple function, and let 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 a1 a2 up to an be the non-zero values, be the distinct non-zero values. Let a1 a2 up to an be the non-zero. I will only choose non-zero in the representation because this will cover zero also, that I will discuss. Be the non-zero values, be the non-zero values, be the non-zero distinct values. Okay, be non-zero, and they are also distinct, non-zero distinct values assumed by the function phi. Now let's define the following sets. Define the set for each non-zero value. We will define a set. Define the set capital AI, which is equal to x belongs to x such that x belongs to x such that phi of x is equal to AI. So we will see that these AIs, they are measurable sets and they are also disjoint. First we will check they are measurable. This is equal to, you can see this is equal to phi inverse image of the set singleton set AI. Okay, this is the inverse image of this point. We are trying to find out those points such that the image of those points is equal to AI. So that means this set is actually the inverse image of the singleton set AI. And we know that the singleton subsets of a real line R, they are measurable because they are actually finite sets. Every finite, they are closed. Sorry, every finite subset of R is closed. So that means this singleton subset of R is also closed. This set is a closed set, and we are taking the inverse image of this closed set, and it's given that phi is a measurable function. Therefore, by definition, inverse image of every closed set is measurable. In particular, inverse image of this set is measurable. Phi inverse of AI is measurable, which is measurable, which is measurable as inverse image of every closed set is measurable, and the set singleton AI is a measurable subset, is a measurable subset of R. Now we verify they are also disjoint. Now we verify that AI intersection AJ is phi, where I is not equal to J, and these I and J, they vary from 1 to n. Okay, 1 less or equal to I comma J less or equal to. So assume on the contrary that this intersection is not equal to phi. Assume on contrary and take some point in the intersection, and take x belongs to the intersection AI intersection AJ, where I is not equal to J. Okay, take x is in the intersection. Then x is in both the sets. This implies x belongs to AI and x belongs to AG. But by definition of AI, whenever x belongs to AI, it means that phi of x is equal to AI. This is the definition of AI. And whenever x belongs to AG, phi of x is equal to AG. You can see it here. It's a definition of AI actually. Where I have to this set, okay? AI is x belongs to x such that phi of x is equal to AI. Whenever phi of x is equal to AI, it means that, or whenever x belongs to AI, it means that phi of x is equal to AI. Okay? This implies this is phi of x, this is also phi of x. It means that AI is equal to AJ while I is not equal to J, which is a contradiction because they are distinct values, which is a contradiction. So which is a contradiction. So as required, because as required, as, so that means these sets are actually pairwise disjoint as required, which is a contradiction as required. Okay. Now we verified that. Next we verified that. Next we verify that phi of x is equal to the summation I runs from 1 to n ai chi of a I of x. This will show that phi is equal to this summation. Again, I use the cases. I assume that suppose x is in some ai or union ai, then I will see this both phi x and this value they are equal. So case 1, if x belongs to union ai, I runs from 1 to n, if it's in this set, then this implies then this implies there exists unique sum m, there exists unique m, there exists unique m such that x belongs to am, and x is not in the rest of the sets. X is not in the rest of the sets. So which implies that whenever x is in ai, whenever x is in ai, you catch this piano. Whenever x is in am, it means that then you can see this x in am means phi of x is equal to am. Okay, then phi of x is equal to am. That's the definition of phi. Definition of am. Sorry, that's the definition of am. And you will see this sum. I runs from 1 to n ai chi ai of x, and x is in exactly one ai, that's am actually, and x is not in the rest of the ais. So the mth term of the sum will be equal to am times chi am of x, but chi am of x is equal to y. That means mth term is equal to am, and the rest of the term is equal to 0. It's equal to am. Okay, so therefore this phi is equal to the summation I runs from 1 to n ai chi ai. Now case second, if x is if if x is not in the union ai, I runs from 1 to n. This means x is not in any ai, x does not belongs to ai, for all I equal to 1 to up to n. Then in that case, since x is not in any ai, so that means phi of x is equal, then its value is equal to 0, because ai is a1, a2, a, and they are only non-zero values of the function phi, and x is not in any ai, so that means phi of x must be equal to 0. Then phi of x must be equal to 0, and the summation ai chi ai of x I runs from 1 to n, it's also equal to 0, because x is not in any ai, so each value is equal to 0, each term of the sum is equal to 0. So thus we have this, thus phi is equal to summation I runs from 1 to n ai chi ai. So this is called the standard representation. This is called the standard representation of phi. This is called the standard representation. This is called the standard representation of phi. There may exist more than one. There may exist other representations. See, there may exist other representations of the function phi. There may exist the other representations. There may exist other representation of the simple function phi. There may exist other or more than one. There may exist other representations of phi. Say, so let's take I can choose one more presentation. Say this one. Say phi is equal to summation j runs from 1 to m bj chi of bj, where bj's are pairwise and disjoint measurable subsets of x. Because in the representation these ai, they are measurable subsets. So again, this in this representation bj's are measurable subsets of x, and they are also pairwise disjoint. You can easily verify that they are actually measurable, because you can see this bj is equal to the x belongs to x, such that phi of x is equal to small bj, so which is actually the inverse image of the singleton set bj. Okay, where bj's are measurable and pairwise disjoint. Okay, so now next we define a step function. Step function. Okay, let's define the step function, which is very important. A simple function phi. It's first a simple function. A simple function phi from x to r is called a step function. Is called a step function. Is called a step function. A simple function phi from x to r is called a step function if phi has if phi has the representation, because it must has a representation, but it must has the following representation. As it's a simple function, it has a representation. If phi has a representation, summation j runs from 1 to m bj chi of bj such that the measure of each set bj is finite. So in some simple function, measure of bj's need not be finite, such that mu star of bj is finite. 1 less or equal to j less or equal to m. If measure of each set bj is finite, then we say that in that case the simple function, our simple function, is a step function. Okay, so I will give an example of a simple function which is not a step function. Let's define this function. Define example. Okay, example example بساعد سليش حمدي كثير عزيز سليش. So let's take this example, the characteristic functions of irrationals Q complement. Okay, it's equal to 1 if x belongs to Q complement, set of irrationals, and its value is 0 if x is in Q. Okay, this function is a simple function because it assumes only one non-zero value, or it assumes only two values, 1 and 0. Therefore, it's a simple function. But the representation of this function is just like this. It's only this one, chi of Q complement. So in the representation of this simple function, we have only one term, chi of Q complement, and the measure of Q complement is infinite. But this measure, but the Lebesgue measure of Q complement is equal to infinity. So therefore the characteristic function Q complement is a simple function. It has only, it's measurable because Q complement is measurable. It's a measurable function, and it only assumes two values, 1 and 0. Therefore, it's a simple function. It's a simple function, but not a step function. But not a step function. But not a step function. Okay. So if you can easily verify that the characteristic function of rationals is step function. So there is one more example, that's the characteristic function of rationals. Characteristic function of rational numbers. Okay. Chi Q, the characteristic function of rationals. Easily verify this characteristic function of rationals is a step function. It's very simple. It's a step function because this is a simple function, and this is also the representation of that function in terms of the characteristic functions. And here the Lebesgue measure of Q is 0, which is finite. So it's a step function. This one. It's a step function. So next we defined the integral of a step function. Okay, integral of a step function. So integral of a step function. Integral of a step function. So let me first explain it so that I will extend this result to general step function. Suppose we have a function f on the interval say 1 to 5 to r, defined by f of x is equal to say its value is 2, 1 less or equal to x, less than 3, and suppose its value is say 5 if 3 less or equal to x and less or equal to 5. Then what's the integral of this function? Then what's integral? 0 to, it's 1 to 5. The integral 1 to 5 of f of x, you can see its value is equal to, it's actually a step function. You can easily verify this. It has only two values, and you can say this. I will first write its standard representation. Okay, then I will calculate its integral. I will write first its standard representation. Then this f, it's equal to twice characteristic function of the interval 1 to 3, open on this, plus 5 times characteristic function of 3 to 5. So therefore this function 5, therefore f is a step function, because it's a simple, it assumes only two values. It is also measurable function, and the Lebesgue measure of these two sets is finite. Lebesgue measure of this one is 2 and this one is also 2, so it's finite. So then f is a step function. Then f is a step function. Then f is a step function. And what's the integral of f? If you want to calculate this, as you are already aware of this integration, it's equal to integration 1 to 3 f dx plus integration 3 to 5 f dx, and that's equal to what's on this range. The value of the function is, it's 2 twice dx, and plus on this range 3 to 5, the value of the function is 3 times dx. You can see this, it's 2 and 5, sorry, 2 and 5, 2 and not 2 and 3, it's 2 and 5. Here it's 5, it's 2 and 5, 2 and 5. This is equal to, you can see this is equal to 2 times this 3 minus 1, okay, plus 5 times 5 minus 3, or you can say this is actually equal to, you can write this as 2 times the Lebesgue measure of the set 1 to 3, okay, 2 times the Lebesgue measure of the set 1 to 3, plus, because the Lebesgue measure of the set is 3 minus 1, plus 5 times the Lebesgue measure of the interval 3 to 5. So that's this actually, that's the, in terms of the Lebesgue measure, I have written this integral, value of the integral in terms of Lebesgue integration. So this is the value of the integration, and you can see you can if I will write it here, this so actually you have written this implies, if you want to elaborate this here, this implies integral 1 to 5 of the function what's this, 2 times the characteristic function of the interval 1 to 3 plus 5 times the chi of 3 to 5. So value of this integral is equal to 2 times the Lebesgue measure of this set, and then its value is 5 times the Lebesgue measure of the next set. Okay? So this is the representation of the function, first standard representation of the function f, and its integral is equal to 2 times the Lebesgue measure of this interval plus 5 times the Lebesgue measure of this interval. Now we will extend this notion of integration to general step functions. Okay, we will try to extend this notion of the integration to general step function. Okay.